question as well as live questions. So let's take up the first assignment here, which is a general assignment here. It's not a specific to Python language, but to get the feel of all the programming languages now, which are now most popular nowadays here. So these questions will give an insight into what they call how to understand them quickly here. So you cannot just believe the statements as somebody says now use this language or that language. You should be aware of why I'm really picking this language now, what are strengths and weaknesses now. That only comes up if you really understand inside of what they call this languages and everything. So the general assignment is designed to really give such kind of understanding here. So let's take the first question here. What are the differences between compiler, interpreter and hybrid translator? First of all, so the kind of programs we write it up, either Python program or Java program or C, CPP or Scala program here, these are called application programs now here. And the kind of programs I'm asking out here, compiler, interpreter and translator, these are all system programs here. They facilitate application programming in a simplified way. But what are the specialties of this? The idea is simple. So this is all, the machine we use it out here. If you look at our computers here, so there are three components in our computer here. One is RAM here, and the other one is multi-core processor here, and there is a disk storage also here. There is a communication between processor and RAM, and also there is exchange of data between a disk and also what they call RAM. First, always understand hardware, because that's how the machines are, everything software is written on top of it. To really understand this compiler, interpreter and hybrid translator, you should understand what kind of machines we are using first of all. So what kind of software we are writing, to really use this kind of machines now. This is a simplified machine. I'm not showing GPU as well as what they call its own RAM here. Only CPU or the core processor here, multi-core processor here. And this is a secondary memory here, and this is going to be primary memory here. So what does this machine can understand? So how do really what they call use this as a computable machine here? So you write a program normally stored in a disk here, but this program you need to write in your high level language like a C language, Java or whatever, the Python or a Scala. So why are you picking these languages now? So the multi-core processor, the understanding of this processor is only the low-level instructions. If you look at the processor chip, the way the physical hardware circuit is designed, they can only understand here a bit-level programming here. That means if I use some zeros ones combination to tell, this is what they call 101010 add means now. So in the manual they will tell you this 101010 means add. And these are the operations now. Now addition is performed inside the processor. The processor, the only capability is going to be machine language. There are a bunch of instructions now. The instruction set is available. There is an instruction set for every processor. If you are using, let's say, the Intel processors now, if you look at their what they call manual, you can understand their instruction set. Or if you are using AMD hardware here, you look at their manual to understand their instruction set, or some other processor, same thing here. What do these guys do here is they can only understand machine language. So this is what they really mean here. There is an add instruction, there is a subtraction instruction, there is a multiplication, there is a jump instruction here, there is a call instruction, there are a lot more here. So, and each of that again add is for our understanding purpose. In their manual, add they assign some kind of a code, operation code. So the add means some number means at binary level, some kind of bit representation now. Like this, everything is a binary level here. If you want to use this machine now, I can do one thing here. I can able to write that kind of machine level program, now ask to execute it up. So the instructions are always available. So then what they call, then we got to load into this processor, execute this first instruction. So any program while executing what they call, if you want to execute, just instructions are not enough. Addition of what? You need the data also. That's why. So while running program here, we always has to really need two things now. So there are two parts we are always interested out. One is called code and other is going to be data. So this is compulsion. So even if you don't write what they call Java, CPP, all these programs here, write a simple machine level program. So to execute this program, or you got to load into the RAM. Why we are loading to the RAM here? Because so if you want to access from disk to this a processor anyway, disk access is very slow. This guy is super fast because instructions, the clock speed of this so-called multi-core processor, that's how the fastness of processor we always analyze. There's a clock frequency. If you look at your computer, the specification of processor, they'll give you a clock frequency. They tell you number of cycles per second. A cycles means here, for each instruction at the lowest level hardware level, how many cycles at the lowest level are required. If the clock speed is very high, more cycles we are getting up per a unit interval. That means more instructions are executing. More instructions are executing means now fastness we are able to observe it up. That's how any processor will say is a higher or lower speed and everything. But that's the way normally that's how the processor work. Now the data is available, code is available. So the data you have to specify each instruction now. So maybe you can give a data name of the variable. If you want in a high level programming language, you create a variables. But if there's no variables, nothing here. Here itself in a machine language, tell data section. This symbol means this variable, or one more symbol, one more symbol. Those symbols you try to use in the instructions now. That means the primitive style of coding here when machines were discovered initially was this kind of coding here. That means programs are written in the machine code, but separation is always available. People have to understand this machine code and everything. And that's what ideally they got really write a bunch of instructions to perform a task. But this is what lowest level thing, and disk we never access, always load into the RAM because RAM is much faster to access than disk now because of the way the design is made for both these memories. Cost also, RAM is higher compared to disk. Processor speed, even though it's much higher than RAM, but it's far better to really what they call use RAM instead of disk. So there's other circuit also will cache, but all this is to improve performance, is irrelevant in this context. But to just give an highlight of what is a primitive style programming, this is what we got to do. Now the question is, it's hard to write programs by using these low level instructions now. That's why we discovered something like high level programming languages. C was one of the initially successful programming language which people love it up because they need not worry about these low level instructions now. But such programming language, how can this machine can understand? There's no way it can understand it up. That's why people have written a programs called a system programs now to facilitate. So all this application development now here, any kind of application program, if you want to run on the machine now, we got to translate into the language where these machines can understand it up. The only language they can understand is going to be the machine language. That's why the compiler program is, the essence is going to be, given a C program or CP program or Java program or any language, you try to translate into low level language now. That's what the whole essence of compiler. So let me show you the process. So first normally use IDE here. Take some kind of IDE, C or a C++ IDE. Then we write a program here. Let's say this is .c or .cpp. So first you have to give this program to a software or a other program which is called compiler. Depends on which language that specific compiler you must require. What does compiler does? Compiler converts this program to something called what they call a low level language here. That specific file they call it as an object file. This is what initially what happened up. So the reason why we are really understanding this compiled languages definitely helps us what they call to understand interpreted languages. Why some language is slow? Why it is some language is faster? We cannot understand the top level without going inside of it. So that's why this life cycle, apart from along with the so-called programs I'm asking, interpreters, translators, and all of that, both of that inside when you keep going up, you can easily you can able to comprehend why is a particular thing is slow in a language and a vision. That's why. So I'm taking up the whole picture. So this is a CCPP, write IDE, you compile it up, you get an object file. The object file is definitely is going to be a machine language code. But so why can't run this object file straight away? The structure of the object file is simply two pieces will be there. One is code section will be available, code section. Another is going to be data section. There's one more section is also available where, so and code data, So is all the code thing here, normally the way you expected up in the lowest level. But this is not enough here. The compiler is not enough here in reality to execute a C program. The reason is going to be your C program might use a library from printf statement or scanf statement, CPP library, or using cout statement. So I'm taking CPP first now. Later on, I'm going to go for other languages now. So but those guys now, they're in a different function, maybe stdio dot, so what they call other header file, they're actually designed. There are something called libraries are also available here. Most of the languages. The repeatable functionalities they keep in the library here. That's where you can have a stdio dot, what they call, so the object file and everything. And also there's other files now, console input output here, dot object file. So the lot more depends on the language. So but these files, where are they available? They're not in a program. You are normally include up a header files now to tell the syntaxes to the compiler, so that compiler will check the syntaxes here. That means here the include what you do it up in C programs, CPP programs. They doesn't bring the code, they only bring the syntax here. So compiler can verify wherever I'm using scanf printf is syntactically correct or not. That's what compiler job, obviously. One of the job is syntax verification. Of doing that, we got this code, but still in this code, we do not know where this so-called printf statement code, scanf statement code is available. We do not know. That's why compiler will tell that I don't understand these symbols now. Some other program will come and resolve that. So that information is all they're going to keep it up in the separate section. So here we keep something called a tables now. Mostly you call it as a dictionaries anyway, key value pairs. Sometimes they call it as symbol tables now. Which symbol you don't understand, which symbols you're already aware of that, and data part, which symbol, part of this so-called object file and everything. They'll store that. Compiler does this work. Now once this object file is there, still the program is not ready to execute because a lot of references are not linked out. Hence this program is really going to pass to one more program here, which is called linker here. Is other system program. So the purpose of linker, the name states here, is trying to link up the library code to the references which are not resolved by this compiler and everything. That's why. So linker look at this information, what compiler place it up, and try to go to the location of this libraries where they are available. If you are using Windows now, at one location, the libraries of what they call C will be available. So maybe CPP you are using, again there is one location where CPP libraries will be available. There's compiled to specific hard machine anyway, your Windows and specific hardware, x86 64 or some other hardware. They're all properly compiled to that machine, they will be installed. That's where, so those locations linker knows now. Once linker knows that location now, go to this guy and try to go into the code, try to resolve those references now. So that resolve references, if we do statically, we call it static linking, but if you do it runtime, we call it as dynamic linking here. Assume initially to understand things easy way, static linking. So the code is actually coming up in place. Now the code is expanded by including all the libraries now. So now the whole part is now all references are what they call completely resolved. That file we are calling out as what they call exe. That's where the output of linker, what we really get it up is technically we call it as executable files. That's what you mean. Someone is giving executable file means now that everything is resolved. So again sections are code section, again is going to be data section. That's what exe file. Some header information still will be there in exe file too. So that's after linking, this is the situation now. So now we don't have any further references to clear it off, but you got to execute this program now. So maybe in your editor IDE anyway, you just click and run. This all happens in the background because your IDE is taking care of all this process because those programs normally are interlinked out here and they know the location of where these are available and it's trying to do the work behind scenes now. This all happens automatically. But you got aware to really get a clarity on what is happening behind each language execution level. Now CS and DS now, but then how am I going to bring to the RAM now? This is still exe file. So I just want to execute the program, but where do I load it up? So we do not have any control where to load it out here. That's where in a RAM there is a special program called operating system here. So let me just rewrite this operating system. The top we have a RAM. This operating system. Now someone has to ask you, okay guy, I have a program to execute now, give you some kind of resources to execute it up. That's where one more program we'll normally see here is going to be loader. One more system program, interact with OS, try to give us the request anyway. Then OS knows now the resource of the machine, RAM resources they know. That's how they're going to really allocate what they call some kind of free space now to bring some part of the program. So that's how ideally you get a space in RAM. But while bringing to the RAM, your program is expanded slightly. So not just one code and one data, this data section further expands to multiple sections now. Maybe if I just write it up a little more detailed way, if this is our total what they call program, this is the code section. Data section will have two more sections extra. One is called stack section and other is called heap section, and other is called a global or static section. Static section. So all these three are meant for data. This is just for instructions. And why do you bring those two extra sections? Because they are runtime memory now. So we don't need what they call that memory until the program starts executing them. But here, whatever the data variables section we can see here, these are all global or static. In compiler level, they can able to see that. So they can able to specify, these are the locations, these are the what they call relative addresses where I can able to keep this data on. But the stack, only when function called up, only that's where the stack is required. When you make a malloc statement or new statements now, I need a heap section. This all while running we require. That's why while bringing to the RAM here, the extra sections gets allocated up. But they may not be contiguous the way I have shown it up. They're all distributed across the memory here. So via something called paging here. That's why OS knows now how to really give up memory to a particular program here. Any program, tomorrow CP program asks here, one more guy, Java guy asks now I need a memory. OS manages memory by using some its own internal algorithms now. That is called memory management algorithms now. They maintain some data structures internally where the free memory is available. Obviously, when you ask for request now, they go into the data structures, find out the right pages available and try to allocate for a program. They're all distributed, but still OS will link all of that by using some kind of, again, data structure. That's why operating system software is also manages the whole resource by using data structures only. So that's a lot of memory is required for OS also to keep their own data structures too. But that's a black box to us. Now, so once given OS now, OS will, there's not only one program, there are a bunch of programs now, processor is there. So OS have internal scheduling algorithms now. Whenever the CPU is freely available or a time slot is over, they keep switching up, try to execute the program. Once the program execution is over, then we inform to the OS that now our execution is over, so free this memory out, take up this memory, then that memory can be used for other programs now. That's what ideally we're saying it up, how a program normally will execute up from start to the end point. But I told you again, if you go to machine level language days now here, we don't have linking, we don't have libraries, all of that. Maybe all of that we manage within our code by ourselves now. We don't have any such kind of sophisticated programs. But once this computing becomes more and more wide acceptance now, people feel that machines can be used for computational work. That's why system programming becomes one of the need of the hour. So when CCPP programs, when people have used up, there are the three internal components, they're going to really have it up. Compiler job is to translate this code section, doesn't know where the libraries are available for linking purposes here. That's why only two pieces they're going to give it up. But a linker's job is whatever references are not resolved, mostly the method calls now here, all these resolutions now is given by this linker here. Once the linking is done, so if you assume static linking, the code actually comes to this place now. Now whole thing is ready to execute. Some information about what is inside, header will be there for every file. exe file also have some kind of header information. Loader's job is to bring it to the RAM or with OS now here, so get the space, start giving a request to OS to treat them as a process. So that means a program which is just a simple a static thing now becomes a dynamic thing here. Once OS it gives up what they call some kind of a ready thing, or maybe some kind of space for execution process now, execution purpose. So a program in execution mode we technically call as process. So all these things while executing here, we call them as a process. Once things are over, all I see is a simple static program. That's what a program, a process, a bunch of system programs which are helping to really get this work done. And once the whole thing is finished up, now you can get some results on console or a file, whatever you can write it up. So this is what you mean by a compiler now. If you see the compiler job is only this part. Linker loaders are still necessary. Now if you understand, see here, the biggest pain here is going to be, if I want to get a compiler, if you want to install a C compiler, what should I ask now? C compiler for what they call my hardware, because this is definitely machine code now. Object file is having completely machine code. That means this is dependent on hardware, no doubt. So depends on hardware. And also one more important thing here, compiler is going to be, so a library, C libraries, you are giving some API, but when you really translate lowest level here, which kind of OS call I'm using? Let's say I want to work with files, for example. If you want to work with files now, C library we have a file system call, but when I'm really doing on Windows system, they have a different kind of API. So that means what? Files to access anything here, ideally programming language gives a control via some kind of library on top of OS system calls now. That means, well, translation now, even OS dependence is also available. Not only hardware, OS also matter. This is what you mean by system. So whenever someone says that I need to bring a system dependent, what is system dependent? System means here the combination hardware and operating system. So if you want to bring a C compiler, CPP compiler, you always have to take this into consideration. Is it so Windows specific and specific hardware? Is it Linux specific and its hardware? Because the translation process is dependent on both of these guys anyway. That's why we got to find the right compiler, otherwise that software is not going to be useful for you. This was very good in initial days now when programming was very painful with the lowest level programming here. But this process have some deficiencies anyway. So one thing here, so this is faster because definitely slower than low level programming, assembly level programming here. Because these instructions, whatever is coming out here, straight away we are writing it out here, they'll be executed out, is all straight calls inside of, from the processor instruction. But when it comes to C language, it's convenient, no doubt. But the reason why it becomes slow is, since they give a very comfortable thing now, when they compile it out, they still come to the machine level language now, but the kind of order they really give it up may not be the as efficient way you can able to write lowest level. There will be some kind of compromise will be available. That's a slightly little difference you can able to find it up, but still it's very, very close to the hardware level. That's a C program directly comes to hardware, so and these instructions are executed up, so super fast. That's why any CCP programs you see it up, fastness you can see a very, very super thing. And if anyone wants performance thing, go to CCPP. This is the reason why they do. Some issues are there because they are dependent, on machines now. Each machine I would really find up a separate compiler, to do that. Linker loaders are required here to really interact with this, operating systems too. But whatever the machine dependent system software, if you install it up, this life cycle is smooth. Now, if you come to the Java world anyway, Java is trying to address a different problem where, so we don't want just a local executions now. What about what they call a independent execution across machines now? Whatever hardware, whatever OS are using it up, why is your program dependent? This I cannot carry to other machine. This object file, if I go to the Linux machine, or if you go to the, let's say, other AMD hardware, then this program don't understand, because the system calls are different and also the hardware instructions are different, and that's why this is not portable. So this portability is the biggest problem for CCPP. They are specific to that machine only, so that specific system I can say. Once compilation is done, that's it. It's all hardwired or locked into that system. But when I want to port this program, I don't want to give source code. My compiled code, if you want to port it up, CCPP doesn't have any way to really get it out. That's where, so Java really try a different approach. Later on, the Java program lifecycle, scalar programming lifecycle, which are called VM-driven lifecycles. Now, I'm going to give up the detailed, diagram here. But at this moment, so that's all the positives and negatives now. So all lowest level, but the way it comes out may not be as good as the way you write it up directly. and second thing is going to be, so it is all locked into the system. So non-portable programs here, compiled programs. If you want portability, give source code, give the your actual logic, direct source files now, recompile, so then relink it up, then you get exe files which are specific to that system here. That's the first thing we want to talk about. I think the question to question 1, I'm trying to interlink. The compilers is definitely part of this life cycle, and C and CPP here explain the program life cycle in detail. This is the detailed program life cycle. All the softwares you are really learning it up in your, in your computer science, learn it up. They are part of this life cycle. So OS is also a very important piece now here, and why this memory extra sections are coming here you should know. And while compilation now, how many sections are available, and how these compilers and linkers and loaders will interact is all by using this specialized place in each of these so-called intermediate files you're getting it out. So that specific detail we are not interested up unless you want to really build up compiler, linker or loaders anyway. So all you got to know here is at least how these programs coordinate to get what they call a programs executing smoothly. That's what you have to really get a clarity. So that's what second one. So compile language like C and CPP explain the programming lifecycle. This compilation process, sometimes we call it as a build process. What do you mean building a project now? So it's only single file, it's okay. What if you have hundreds and thousands of files are available? They have interdependencies now. So this is where a building is also necessary. For building the project, in reality, we just don't use compiler, we use some tools for building as well. Let me add that also in the life cycle. You get a clarity on the project level, how the things will happen. Now I'm going to bring it up. One more thing here. Let's say I have a file. This is all a bunch of C files now, for example. Now I want to execute these files together. First you have to give it a tool called what they call a builder innovation. A builder. So what does builder will do here? So builder will use definitely compilers, no doubt about it out, but after using this compiler internally here, they'll create again the lowest level code innovation. They try to use something called compilers internally. But how does builder knows now how to really compile these projects, which order? That's why they are going to use internally a graph structure. They try to make a dependencies via some kind of graph data structure. By using graph, they know which order they have to execute it up. So any builder tool, see you have a lot of build tools now. Make is one of the old tools. Later on, the lot more tools are available. Java guys have a different builder tool. And again, so other compile languages have a slightly different compile tools now. What are the tools you are going to use it up? You must translate first into this low level code. Only then the remaining section actually continues innovation. That's why building a project is necessary for compiled what they call languages now. So and when multiple files are there, we call it as building. We don't call simply as a compilation now. That's what. If you builder have access to this other guys also, linker and loader, all of them together share, that's really good. Then we can able to straight away make call to OS. It's how these softwares are combined together and how they distributed up is a different story. But internally, whatever software you are going to use it up, these pieces are going to work together in a coordinated manner. So this is what ideally we mean. Now the pain point in building. So one of the questions also I have seen in our portal where so people ask here, why is this why does the building takes a very high time? Because of this. So to build a project now, if I do small change in one C file, again which are dependent and all, they have to recompile it up. So compile languages here, one of the pain point here is building. You have to translate to the lowest level is the first stage. Only then execution starts. If you cannot translate, you cannot compile and convert into low level code, no execution at all. Without building step here, that's where you cannot continue further at all. That's first and foremost aspect. You understand as a C project or CPP projects. So that's what the complete clarity. So I want to give up in a question 2. Now, so we understood compile languages. Now we want to understand what is interpreter innovation. So again, to understand interpreter, first you take a programming languages where interpretation is supported up. The same way I have drawn life cycle now. We are going to draw the life cycle for interpretations. And also after that, there's a hybrid languages are also available where both compilation and interpretation together they are available. There's other special programming language, recently you must have seen it up, TypeScript, that follows a slightly different approach. So if you want to really understand all of that, first you need to understand the very old things, how this is happening, how this improvement revolution actually happened it out. So in this session, I just want to give this view. So just go through this process and take some projects now. Just observe the life cycle now. You get a clarity. In the next session, I'm going to give clarity on interpreted languages and hybrid languages. Then you'll understand why compiled programs are faster. Why not interpreted? All the reasons will be clear if you get a clarity on this. So I think that's all for today. Now I want to really talk about it. Maybe one more question I can take it up. So what is the difference between language specification, language implementation? Language specification, language implementation, CCPP level. Later Python also will see it up. So people say that, so ANCC, what does it mean? So the mean here is going to be, ANSI is a, what they call an organization where people, some companies are really make what they call consortium. They come up with what they call specification. What features a C language, compilers must support it up. They try to give a theoretical, a descriptive manner, more precise manner here, the kind of features a particular version of C language they're going to support it up. If you see for example 90 or C for example 95, what does it really mean? The revised versions now, when the need comes up, if you want to push language further, they come up with this, add these requirements in standard. The standards now you can able to implement by any company. Let's say if I'm a X company, I'll take this standard, I'll implement according to standard. I'll tell you our compiler is ANSI compliant. Or if one more company will take the same standard, they implement their own what they call, they do their own implementation. They'll say that they're also ANSI compliant. Again, they'll tell you which specification they're compliant. So ANSI C95, ANSI C90. Look at CPP now. How many versions we got it up? CPP 11 you must have seen. CPP 14 are there. CPP 15 are there. That means languages keep on expanding it up. Maybe they want multi-threading, they want functional programming. There are a lot of changes happened over a period of time. That's where, so the specifications are very important. You cannot really go to a specific compiler, execute the program, say the output. That's not correct. You always have to go to specification. Look at the spec. What this guy's expected behavior. And if they say you can write your own, they're dependent, you can have your own what they call, system dependent output. Any compiler can write their own output. That's why always specification first, then we need to go to the what they call the actual implementation. Python also same thing, Java also same thing here, or any language in this world. That's how it is going to work. Otherwise, everyone will have their own things now here. Very difficult to get interoperability here. That's why. So specification versus what they call language implementation. This you need to be aware of that. So little later Python and also Java I'm going to talk about in detail. Which programs are faster? Again, you need to wait for one more session to get clarity by yourself. Alternatives again later we are going to see it up. That's all we want to really talk about. Few of these first assignment questions now we'll discuss. Remaining questions will continue for next session innovation. So that's all about what they call. So we want to talk about as part of this session here. So you just observe this now here, whatever experience you have it up next week here. So I'm going to give a life cycles for other types of languages, interpreting as well as hybrid languages here. Then with that we can answer the pending questions. So any questions I'll see live here. There's no more questions here. So that's all for today here, what we want to discuss for Python.